All right, so let's take a look here. We have lesson 5. This is from module 2, and it has to do with predicting from lines of best fit. So for this one, we're going to take a look at some lines of best fit, utilizing those lines, and then we're also going to take a look at calculating correlation coefficient using our calculator given a set of data. So first thing here is we'll just read through what we got, and then we can go from there. So predictions on lines lines of best fit. So it says a scatter plot shows the relationship between two sets of data, which are written as ordered pairs and then graphed as points on a coordinate plane. A scatter plot can be used to identify trends or correlations in data. A line of best fit drawn through the points in its equation can model that relationship. The line of best fit in the form y equals mx plus b can be used to predict the values of y based on the values of x. So what we have here is a line of best fit, right? It's a line. So we write it in the equation y equals mx plus b. Now, this line of best fit isn't an exact line, right? We use it to model a relationship, but if we take a look at our scatter plot down here below between number of phones and number of cars, right? There's no one line that can go through all those points there. Therefore, our line of best fit won't be exact. So here it says, in the following example, the equation of the line of best fit will be used to make predictions. You can check with your teacher or refer to your graphing calculator manual to be sure you know how to find the equations for lines of best fit on a calculator. So I'm going to show you that using our TAI Inspire calculators. So it says, suppose that a researcher is studying the relationship between the number of telephones a family owns and the number of cars a family owns. His data are shown in the scatter plot below. So let me scroll down here a little bit. So here we're looking at data, and we have number of phones and number of cars. So it says, using a graphing calculator, a line of best fit given by the equation y equals 0.78x minus 0.04. So what they did, right, is we're going to look at this as a different problem, but they put in all of these different points as into a table on the calculator, then calculated using one variable statistics, the line of best fit, right? So if we're looking here at this point, just for example, right here is our x value is 6, and the y value, if we look over there, is 4. So when we're creating that coordinate would be 6, 4. When we're putting it into a table, right, we would put it in the domain, and we had the range, and the domain would have been a 6, and the range 4 for that corresponding point. And we'd go through and do that for all those points. But for this one, they already gave us the line of best fit. So then it says, the equation can be used to predict the number of cars owned by a family with 5 phones. So what they did here is they took the equation, y equals 0.78x minus 0.04. And they wanted to find the number of cars owned by a family if they have 5 phones. Well, if we look at our scatter plot, we see that phones here are on the x-axis, while cars are on the y-axis. So we're going to substitute in 5 for our x and find out where that would fall on the number of cars here. So if we were to write that out, we'd say y equals 0.78. Then we're substituting in 5 for the number of phones, then minus 0.04. And then if you work that out, you get y equals 3.86, which predicts that a family would have 3.86 cars, right, if they had 5 phones. But given that you can't own 3.86 cars here, right, it probably makes sense, as they say here, to round up to the number 4. So the slope and y-intercept of a line of best fit often shows something about the relationship being modeled. The slope measures how much change occurs in the y variable for every 1 unit of the x variable, right? So that shows as the number of phones change, what happens to the number of cars. So if we increase the number of phones by 1, right, the number of cars will increase by the slope, which is 0.78. The y-intercept shows the expected initial value of the relationship when the x variable is 0. So here, this is our y-intercept. So what that's showing is that if a family has 0 phones, then they most likely, if we look at that number there, have 0 cars. All right, take a look at the next page here. It says, in the example with the phones and cars, the line of best fit, right? So just like I was talking about, the slope is 0.78 and the y-intercept is 0.04. So the slope shows that for every increase of 1 telephone a family owns, it can be predicted that the number of cars the family owns will increase by 0.78. And then, like we said before, the y-intercept also being close to 0 shows that if the family does not own a telephone, they are not likely to own a car either. One of the keys here is to find slope, right? Slope, we use our formula, which is the change in y, or y2 minus y1 over x2 minus x1. All right, so as we keep going along here, it says, the results of a survey of 8 engineers are given in the graph below. And it says, A, draw a line of best fit through this data. So again, we can plug this into our calculator and calculate a line of best fit, but to be honest, this question doesn't give us good data points here, right? So we know that this is somewhere between, this is probably about 1 year experience, and maybe it's 41 or 42,000 in terms of salary, but they didn't give us exact numbers. So here we're just going to estimate a line of best fit. I'm going to choose my line tool here. So when we estimate a line of best fit, right, we want to try and draw a line that goes close to most of the points here on our graph there. So this one has about the same amount above and below, right? It's pretty similar to what they have down here, but basically we're just drawing a line that shows that general trend. So then it says here, according to the line of best fit, what is the salary of an engineer with 15 years experience? So if we want to find 15 years experience, we're looking on the x-axis for where 15 is. And 15 is right halfway in between 10 and 20. So here what we want to do is take this and then just go vertically until we hit our line of best fit. It hits our line of best fit right about here. Okay, so that would be our expected salary. If we go over to the y-axis here, we see that it's somewhere between 50 and 60, closer to 60. In this example here, they said that it's about 56,000. I would agree with them if you said 57,000, that would be fine. 58,000 even would probably be acceptable there based on your line of best fit. So when it was given in this problem here, they didn't want us to find the exact numbers here. So anything around that range would be good. So we keep moving on here. We're going to take a look again. So now they gave us a scatter plot that shows the relationship between the number of floors above basement level in an office building downtown and the height of the building. So the equation modeled below, y equals 19 over 2x plus 10. So which statement can be predicted from the equation that models this line of best fit? So here we're showing the relationship between the floors and the height of the building, right? So the floors are going to be our x value and the height of the building is going to be the y value. So here it says the height of the building. So remember, our height is our y with 1 floor, which is our x, is 19 over 2 feet. Well, if we were to take y equals 19 over 2x plus 10 and substitute in 1 for x, we'd have y equals 19 over 2 times 1 plus 10. This here, when we add these together, 10 plus 19 over 2, which is about 8.5, right, is not going to be 19 over 2 because we're adding 10 to it. So it's not A. Here it says the height of a building with 1 floor is 10 feet. Well, we just found the height of a building with 1 floor is actually going to be 19 over 2 plus 10, right, which is going to be, oh, sorry, that's actually 9.5 feet, is going to be 19.5 feet here, right? So that doesn't work either. Here it says for every increase in number of floors, the height of the building increases by 19 over 2 feet. So every time that our floors increase, does the height increase by 19 over 2? And that's going to be our answer here, right? Choice C, because what they're saying is the slope. The slope shows that for every 1x that increases, we multiply that by the slope, which means that the overall height is going to increase by 19 over 2. We take a look here at choice D. It says for every increase in number of floors, the height of the building increases by 10 feet. No, the height of the building, the constant, right, is 10 feet. So it doesn't increase by 10 feet more each time. It actually increases by the slope, which is 19 over 2. All right, now moving on to correlation coefficient. So correlation coefficient is an R value that we find it in our calculator, and it measures correlation. So correlation here, if we take a look, is a measure of the relationship, right, between two variables. The correlation coefficient measures the strength and direction of the linear relationship. It goes from -1 to +1, and it's denoted by the letter R. So when we're talking about the correlation coefficient, we're talking about different things here. So when we have, say, like a number line, I'm going to put a -1, 1, right in the middle, we have 0. And then we can add in, usually it's -0.5, then +0.5, and then usually 0.75, 0.25, -0.25, and -0.75. So if the R is positive, then it shows that the X variable increases, the Y variable also increases. So if we're positive here, right, this is also similar to a slope, but if we're positive, then our correlation coefficient, our data should be generally going up in that direction there, right? We have an increase of slope, and then the closer together our dots are to forming a straight line, the stronger the relationship. So as you get closer to 1, it's stronger, and on this side, it's all positive. Then here it says R is negative if, as the X variable increases, the Y variable tends to decrease. So if we were looking at a graph for negative, right, we're seeing that most of the points generally are going down. As our X value increases, the Y's are going down. So we still have a strong correlation the closer we are to -1, but on this side of 0, right, it's a negative correlation. Then it says if R is closer to 0, then we have a weak linear relationship. So if we're at 0, right, these lines or these points don't necessarily make up any line. There's no one line that we could draw to model these points here. So as we get closer to 0, it actually becomes a weak relationship, and even at 0, it would show no relationship. So as we get farther from 0 and closer to +1 or -1, right, it becomes stronger. And if it is at +1, it would be a solid line. All the points would make one straight line. And same thing for -1, they'd all make one straight line. It's just our slope would either be positive or negative. So down here it says, in a linear relationship problem, determine which variable represents X, which variable represents Y. And then once that's done, we can use our calculator to find the correlation coefficient. So we're not going to use a TI-84 plus. We're going to use a different one that we'll take a look at. For 2 of the problems, we'll actually use the calculator, and I'll pull it up here. All right, so going on down there, we're going to skip these steps up here because these steps aren't related to the ones that we're going to do. And what I'm going to do is pull up the calculator and use this set of data to find the correlation coefficient. So when we're looking here, right, it says the data below shows the relationship between a number of years a company is in business and the number of advertisements they put in the local paper each year. So our data is going to be an X value and a Y value, with the X being the number of years in business and Y being the number of advertisements. So for our first one, the X would be 1, Y would be 36. So let's pull up a calculator. All right, so when you have your calculator here, we are going to start with our blank screen, right? We can go to home. We want to do new. And now we want to do lists and spreadsheets. So number 4 here. Then we always titled our first column, right, domain. which is our x values, and our second column, range, which is our y values. So now we're just going to go through, and I'm going to put in all the x values first. So we have 1, then 2, 3, 4, 5, 6, 7, 8. So that again was just the x values from here, right? It was 1, 2, 3, 4, 5, 6, 7, 8. So now we're going to put in the corresponding y values that go with each one here. So the first one is 36, then 32, 5, 16, 27, 40, 12, and 24. So that's all of our data. Once we've input all of our data, we go up to the top. We're going to go and click on C1. So this part here, right? Because this is where we're going to want to populate our linear regression. So on here, it talks about doing the linear regression using the TI-84. To use this Inspire here, we're going to hit Menu. Then we're going to go to Statistics, Stat Calculations, and then Linear Regression. And we're going to choose MX plus B just because it's easy for us to read that line there. Now, our X list, remember our X's, we labeled the domain. The Y list is going to be the range. And then we're going to go through here. So our results will go in D, that's fine. So now we have a look here. This is our linear regression. So we have a slope, which is negative 0.8095, right? Our y-intercept is 27, but we want to find the correlation coefficient. So the correlation coefficient, if we're back here, that's our R value, right? So if we take a look at our calculator, we scroll down looking for R, we see R squared, but we don't see R. Now here is R. R is negative 0.16. So if we're looking on this one here, where would negative 0.16 fall? That's in choice B, right? So our R here is equal to negative 0.16. So now, done with the calculator, don't need it anymore for this problem. So if we're looking back over here, it says, which statement best describes what the R value you found in this problem tells about the data? So remember, we have our range in R values. They go from -1 to +1 with 0 in the middle. The closer we are to the outside, the stronger the relationship. So the closer we are over here, the stronger the relationship. The closer you are to the middle, the weaker the relationship. And then on our right side, just like on the number line, it's positive, and on the left side, it's negative. So here it says, which statement best describes what value of R you found in this problem, tells about the data. Well, our negative 0.16 is going to fall on this side, right? Negative 0.16. So this is a lot closer to the weaker, and it's negative. So if we're looking through here, it says there is a weak negative linear relationship in the data. Probably going to be our answer here, but let's check the other ones. There's a strong negative relationship. Stronger would have to be a lot closer to -1. So you're looking at negative 0.75 and above. So it's not strong. C, there's a weak positive. Well, our correlation coefficient was negative, so it's not positive. And then D, there's a strong positive. Again, it was negative, so not positive. So that leaves us with choice A still being correct, that there's a weak negative linear relationship in the data. All right, so I'll read this and then we can get into the practice problems. It says, when a strong linear relationship exists between two variables, it may be tempting to think that one causes the other variable to occur. However, strong correlation, very important to highlight this in your book. However, strong correlation between variables does not mean there's a cause and effect relationship between the variables. It simply means that the two variables have a relationship that is predictable. So for example, a study might show that there's a strong linear relationship between swimmers on a swim team and the color of their hair being brown, but that does not mean that being a swimmer on a swim team causes your hair to be brown, or that having brown hair causes you to be a swimmer on a swim team. So even if there's a strong relationship, positive or negative, does not necessarily mean that one causes the other. All right, so now it's time to look at the problems. So here is our problem set. When we take a look here, problem number 1 says, a scientist related the age and length of baby sharks on a scatter plot below. So we have all these baby sharks on this scatter plot below. Oh my goodness, I don't think yours comes with these lines. Let me see if I can. Maybe. Either way, it says, based on this, what would you expected length of a 12-month-old shark? So I put in some lines here that I can't seem to get rid of. But the first one I did is I drew a line that showed our line of best fit, right? So if we draw a line here, it goes through most of the points there. And we could see that some of them are above, some of them are some of them are below, which is what we want for a line of best fit. But generally, it goes through that general trend. Then it wants to know at 12 months, right? So when we're at, when we're at 12 months, what is going to be the length in centimeters? So there was no 12 months, right? So if we're looking at our axis here, it stops at 10. So what I did is kind of extended this out to what I thought would be about 12, and then drew a line straight up to see where it crossed my line of best fit. Well, across my line of best fit, pretty close to the 60 up here, right? But not quite at 60. So when I'm looking at these different lengths here, I'm going for the highest number closest to 60, which is choice D, 56 centimeters. So you're basically extending this trend out just by sketching a line of best fit and then seeing where that would be at about 12, right? Because they didn't give us exact data points, we're not going to use our calculator for this one, and 56 is a good estimation. All right, number 2. Number 2 again here. So it says, the scatter plot relates the circumference and height of 10 trees. So which statement can be concluded based on the line of best fit for the data? So when we take a look here, we have our height, right, which is our y's, and then our trunk circumference, which is our x. It says the height of trees increase approximately 1 foot for every 5-foot increase in trunk circumference. So when we're talking here, we're looking at the slope. So choice 1 is saying that the y's increase 1 for every x increase of 5. So the slope would be 1/5 here. B says the height increases 1 for every 15-foot increase in our x values. C says that the height of trees increases by 5 for every 1 foot of increase in trunk circumference. And D says that the height increases by 15 for every 1 foot in trunk circumference. So again, got that by saying the height of the trees is our y, trunk circumference is the x. The change slope is always the change, which we use a delta symbol for, change in y over the change in x. So what we want to do is find the slope of this line. So I'm going to pick 2 points that I think I can see on this line that aren't totally, that are close to being on the line. So 1 point, let's go with this point here. If I look over here, the x value of this point is halfway between 12 and 16. So that's 14. And then the y value, if we look over, halfway between 90 and 120 is 105. And then if I want to pick another point that's on the line, let's go with this one here, is pretty close to being on the line. And that's at 6. And if we go up, and 60. So what we want to do is find the slope using these 2 points and see which one it's closest to. So remember, our slope formula is m equals y2 minus y1 over x2 minus x1. So when we're labeling our points here, right, this is our first point, so this will be x1, y1. Then down here we have x2, y2. Or actually, yeah, it doesn't really matter which ones we do here. So if you flipped around the other way, you'll be fine. We'll still get the same answer. We're just going to be dealing with 2 negative numbers here when we're taking a look, but we'll see when we get there. So here, m equals, so if I take y2, I'll have 60 minus y1, 105, over x2, which is 6, minus y2, 14. So m equals 60 minus 105 is going to be 45, but it's negative. Right? Let me just check this. 60 minus. It's been a long day. Yep, negative 45. And then 6 minus 14 is going to be negative 8. So now if we want to simplify this one out here, negative 45 over negative 8. So when we have a negative divided by a negative, it's going to be positive, and we get that it is equal to positive 5.625. So if I'm looking for which one is most similar to what I have here, we can find these here. So 1/5, if we simplify that into a decimal, it is going to be a fraction. It is going to be a decimal less than 1. Same with 1/15. So not choice A or B. 5 over 1, well, 5 divided by 1 is 5. That's pretty close. Let's see what the last one is. 15 divided by 1 is 15. So the one that's closest to our 5.625 is 5, which is choice C. So what that's saying is that for every 1 foot that the trunk moves over here, right? So for every 1 that we move over, which is half of a block, that means that it goes up 15. There's a 15-foot increase in the height. So as we go over half a block, so from here to here, right, it goes up 15, or sorry, it goes up 5 feet, which makes sense as we're going through here. All right, take a look at question number 3. So question 3 says, the scatter plot below relates the average daily temperature to the numbers of visitors on a beach. Which value of correlation coefficient best describes the data in the scatter plot below? So if we look here and we had to draw a line of best fit, generally, most people, right, we draw a line that goes probably in that direction there, right? So it shows that it's a positive increase, and generally we see a pretty good trend there, right? They're all kind of going in that general direction, and they're pretty close to that line that I just drew there. So if we have a general trend in the right direction, we're looking at a correlation coefficient that's, right, so if we're looking at just positive here, we have 0 and positive 1. Then we have 0.5, 0.75, and 0.25. If we're at 1, every single one of these dots, every single one of these points in the scatter plot is on our line. So it's not 1, right? If we're at 0.25, there's pretty much not a correlation, right? It's pretty scattered. Maybe we generally maybe looks a little bit positive, but you're not going to see 0.25 is going to look pretty scattered. And then if we look at 0.5, it's going to be trending possibly in a positive direction, but it's not going to be this clear of a positive correlation here. You're going to see a lot more that are further away from our line, but generally is showing that line. So 0.75 is a pretty good number here. That's going to show that we're going in that general direction, and that all of the lines that were originally given to us are pretty close to the line of best fit here. So 0.75 is your answer. For 1.0, remember it had to be exactly on the line. And then 0.5 and 0.25 don't show a strong correlation really at all. All right, number 4 says, a scatter plot below shows the relationship between the number of inches of snow, so the number of inches of snow, which is our x values, on the ground during the past winter, and the sale of shovels. So the sale of shovels is our y value. So which statement can be concluded from the data in this plot? Well, if we just look at this graph first, we see that as the x's increase, we also see the number of shovels sold increase, right? So we do have some sort of trend here, right, that tends to be positive and is pretty close to a line of best fit if we were looking here. So which statement can be concluded? The greater number of inches of snow, the greater number of snow shovels that are sold. So what that's saying is that as the inches of snow are greater, then more shovels are sold. Maybe, but this is kind of implying here that there's causation. So this is showing that if there's more snow, more shovels will be sold. Here, it doesn't necessarily tell us that, right? Because if we look here at 15, right, that more inches of snow fell than when we had 9, but less shovels were sold. So this one is implying causation, which is not correct here. Here, the greater number of snow shovels that are sold, the greater number of inches of snow. Again, they're saying that this causes the next one, which isn't true here. C, there is a weak linear relationship between the number of inches of snow and the number of shovels sold. I wouldn't say this is weak. It's a pretty strong relationship. So when we look at D, this is going to be our correct answer, that there's a strong linear relationship between the number of inches it snows and the number of snow shovels that are sold, right? We see as snowfall increases, this number of shovels sold is also increasing, but we don't know that one is causing the other, and that's what A and B are implying. So D is our correct answer because all we can say is there's a strong relationship. Number 5 says the scatter plot below shows the relationship between the number of pictures in the packages sold by a photographer and the total cost of the packages. So if we take a look here, it says, what does the slope of the line of best fit tell us about this data? Well, first let's find the slope in this line of best fit. So right away, I want to pick 2 points that I can work with here. I like this one here, and also that one there. I like this one because it's also our y-intercept, which will help us when we have to write the equation of the line here. So the first point here, if we look, we're counting by 5s on both axes. So the first point is 0, 5, because we went over 0, then up 5. And then our second point, we go over 5, up 10. So 5, 10. So if we want to find the slope, remember m equals y2 minus y1 over x2 minus x1. Here we have our x1, y1, x2, y2. So if we want to continue finding the slope, y2 is 10 minus y1 is 5 over x2, 5 minus x1, 0. So here, 10 minus 5 is 5 over 5 minus 0 is 5, which equals 1. So that shows us that as the number of pictures increase by 1, right, the total cost increases by 1, right? Because here we have a slope of 1, which we can write as 1 over 1, which would show that as the x increases by 1, so does the y. So now if we want to go through here and find the expected total cost for a package containing 75 pictures. Well, first let's write an equation of a line here. So we have y equals mx plus b, right? Our m is the slope, which is 1, and then our b is the y-intercept. If we look at this graph here, the y-intercept, right, is where this graph crosses the y-axis, which is right here, and it's the y value where it crosses the y-axis. So the y-intercept is 5. So if we wanted to write our equation, we'd have y equals, again, our slope is 1, so 1x plus 5. It says, what is the total expected cost? That's our y value, right? Our y values up here are our total cost for 75 pictures, which are our x value. So we're just going to plug in 75 for x and find out what y is. So y equals, 1 times 75 plus 5. 1 times 75 is 1, plus 5 is 80. So if we're expecting the total cost, we'd expect it to be $80. All right, and that's as we go along here, you can see that any of these points here that we pick, the number of or the total cost is always $5 more than the number of pictures, because as each picture increases, as we increase the total number of pictures by 1, the price also goes up at that same rate. All right, so let's go ahead and take a look at the last question here. Number 6. So number 6 has to do with finding the R value. So this time we're going to bring back our calculator and then do a little bit of analysis after we find it. So if we bring back a calculator, all right, so we want to do a new table here. So let's do, we can do home screen again. 1, new, no, we don't need to save it. So we're going to do a new list or spreadsheet. And we want to find the relationship between a cost, right, and the average customer review. So for our A's, we can label that our cost. And then for B, let's do review. And then let's fill in the data. So for cost, I'm just going to go across $145, $219, $105, $98, $165, $249, and $125, and then finally $90. And then if we go through, scroll back up, put in the average customer review, 3.6, 4.5, 3.0, 2.7, 4.2, 4.8, 3.5, and 2.8. So remember, at this point, if you're just watching this for the first time and didn't try it out yet, you can pause the video here, right? Type this on your own. Really take the time to practice it, because it's going to be a useful skill as you move forward in high school here. So then we go back up to the top, C, go to cell C1, and now we're going to calculate a linear regression. So on our calculator, we hit menu, 4 for statistics, 1 for stat calculation, and then we want to do a linear regression. So our X list were our cost, our Y list was the review, everything else looks good, we hit OK, and now we're looking for our linear regression. So using our calculator, we're going down until we find R. Here is our R value. So it says use a calculator to find the R value here. So we find that the R value is equal to, sorry, go back here, 0.97. 0.97. So this is our correlation coefficient. So remember, when we're looking on this number line, I'm sorry, it's a number line, and we have 0, +1, -1. Here it's a strong relationship, weak in the middle. Here it's negative, here it's positive. This 0.97 is pretty much at 1. 0.97 is all the way down here. So it's a very strong positive relationship. So here it says, explain whether the value of R that you calculated indicates the higher the cost of a hotel room causes the average customer rating of the hotel to increase. So here, if we take a look here, again, so there's a strong positive relationship, but we don't have enough data to say that one of these causes the other. So we don't have enough data to say that the more expensive the hotel room costs, the higher the customer rating. So all we can say is there's a strong positive relationship, but we don't have enough data, right? So we cannot say the higher the cost, the higher the price, or higher the rating, sorry. So we can't say that. We can just say there's a really strong positive relationship, and that's where we have to stop because we don't have enough data. All right, so this is the end of this lesson. So I will make a video for the review, and we'll put out some quizzes for this one so that you guys can continue to keep earning your extra credit points. Keep working hard. If you have questions, we are starting to set up some Zoom meetings to go over some of those earlier videos that we didn't go through the practice problems in. So if you want to set up a Zoom meeting there, make sure to reach out so we can get you involved in that as well. All right. Until next time.